Thank you for attending my talk. And the topic is about the fast algorithms for quantum signal processing. And I'm from Department of Mathematics from Berkeley, and it's a joint work, a series of joint work with Xiang who is currently the graduate student in MIT, and Jiasu Wang, who is my colleague in mathematics, and my advisors, Professor Brigitte Willi and Professor Lin Lin. So I first want to introduce why we care about this question, this kind of problem. So one of the most exciting developments in quantum algorithm in recent years is called quantum signal processing or quantum single value transformation. So in a recent paper published on PRX quantum, the collaborators and Professor Isaac Trong, they state that quantum single value transformation can be served as a unified framework that can be grandly unify a large class of quantum algorithms by just slightly tune the parameter called phase factors. So if we just dive into the theory of quantum signal processing, it can be very complicated, but high level speaking, there are just two versions of the quantum signal processing. The first one is the SU2 version, that is a low dimensional version of the quantum signal processing, where we can use the sequential Z-phase modulations to tune parameterized X rotation matrix, which I denote as Wx. And this parameter this parameter called phase factors, once they are given, we are able to find a parameterized form for two polynomials Px and Qx. And those polynomials can be used to implement some functionality on the quantum computer. If we directly solve the SU2 version of as an approximation theory problem, we are able to determine the phase factors phi 0 to phi d, and then we directly use those phase factors into a high-dimensional problem to construct a quantum circuit, which can be used to do the quantum eigenvalue transformation or the quantum signal value transformation. And in this talk, because I'm curious about how we can find the phase factors, so I will just focus on the SU2 version of this problem. So the goal of our QSP, or the SU2 version of QSP, is as follows. So we are given a polynomial fx, which is of degree d, and it should be even or odd. That means the parity is definite. And we also require fx to be uniformly bounded on the interval -1 to 1, because it will subject to the unitarity when we want to implement this polynomial on a quantum computer. And the goal of QSP is to find a set of phase factors phi 0 to phi d, so that if we do the SU2 matrix multiplication and we focus on the upper left block, and we just extract this real part, it will exactly be equal to fx pointwisely on the interval -1 to 1. So the solution is guaranteed to exist due to some nice work by Gilyen, Su, Low, and Wiebe in 2018 or 2019. So once upon a year, the phase factor is recognized to be very hard to compute. In a nice work by Charles and his collaborators, they claimed, in 2018, they claimed it's very prohibitive to compute the QSP problem for the degree which is even greater than 32, that is supposed to be very hard. So this conjecture make a bottleneck to the implementation of quantum single value transformation apart from building the quantum computer. So that means even we have a very correct quantum computer, we are not able to explicitly obtain those phase factors for our quantum algorithm implementation. However, almost the same year, like in Gilyen's paper and the Haas paper, they claim they investigate and quantum algorithm, they investigate a classical algorithm to compute those quantum phase factors by using root finding subroutine of a high degree polynomial. But this subroutine is supposed to be very accurate in order to in order to mitigate the accumulated numerical instability. So if we just use the standard double precision arithmetic, their algorithm is limited to about 100 phase factors, but it's a significant progress because we just moved from 32 to about 100. And 2 years later, in one of my works, we proposed an optimization-based algorithm to solve this kind of problem. So there's no rigorous proof at that time for the convergence of our algorithm, but numerical observation shows that our algorithm is very stable, and using the standard double precision arithmetic, it can be used to compute the phase factors for the degree which is higher than even 10,000. So we just moved from 100 to 10,000 so far. And then just a few months later, some other researchers also proposed another treatment called capitalization. The basic idea is they want to add some more perturbation to the target function to overcome this numerical instability. And there's still no rigorous proof. By using the standard double precision arithmetic, they can achieve like 3,000 phase factors. So there's a very exciting movement that we start from the prohibitive 23 conjecture to about 10,000. And this problem was practically solved within just 2 years. And we also have another work in preparation, and we discovered the matrix product state structure in the QSP problem, and use this kind of structure to simplify our computation and give a local convergence proof, which just complete the story of our optimization-based algorithm. So I want to first talk about what is the optimization-based algorithm for finding phase factors, and then we will dive into the rigorous proof and want to see what is the energy landscape of the optimization problem. To formulate the problem, we should have a target. So in our problem, the target is a polynomial of definite parity, and because we know it is either even or odd, so it literally just have half degree of freedom in this polynomial. And to determine this polynomial of definite parity, we just use detailed points to do that. So in the left panel, you can find a polynomial, and it has some symmetry because it's an even polynomial. So we only have to sample some points on the positive x-axis to determine this polynomial. And in order to achieve some numerical stability, we use the Chebyshev nodes, which is the roots of Chebyshev polynomial. And the structure is very sparse near 0, but it's very dense near 1. And using these samples by using Chebyshev nodes, we are able to formulate our problem because these samples are enough to characterize a polynomial. So we want to minimize the objective function, where the objective function describes the distance of our answers to the target of our optimization problem, fxk, which is sampled on this Chebyshev nodes. So this kind of optimization problem is guaranteed to have a global minimizer because the existence of the phase factor just yields directly there's at least one minimizer so that the distance between the answers and the target is 0. But there's a very severe issue because we are using d plus 1 phase factors. So the degree of freedom in the phase factor is about d. But as we claimed before, in the polynomial, there's just about half a degree of freedoms. So there's the mismatching in the dimension will cause the solution to be very unique. Very ununique. So in order to overcome this difficulty, we introduce a technique called symmetric QSP. So in the general QSP, the phase factor is chosen to be arbitrary. So we have the arbitrary z rotation, phase modulation, and followed by some x rotation, so on and so forth. But it shows that the Q can be a complex polynomial in this system, Well, we are only caring about the upper left block of this matrix multiplication, so Q is not of our interest. So if Q can be a real polynomial, and it doesn't affect the property of P, then we can reduce the degree of freedom. And that is the origination of symmetric QSP. So if we choose a phase factor so that it is invariant under the reversion, for example, the first phase factor is equal to the last one, and so on and so forth, we call this phase factor a symmetric phase factor. By using the symmetric phase factors, our QSP problem gives a polynomial Q, which is a real polynomial. And the degree of freedom is now d tilde in the phase factors instead of d. So it matches that of the target function fx. And we modify our optimization problem to be a minimization problem by minimizing the distance of the symmetric QSP answers and the sample of the polynomials. So let's take an example. If we want to solve the linear system problems, that is very simple, like a 2x2 matrix A, and our goal is to implement the inverse of A. So we know the condition number of this matrix is 2, and we suppose we have some prior upper bound to the condition number of this matrix. Then we know that by properly scaling this matrix, we can make the eigenvalues of A lines completely into this subinterval d kappa. Well, it is interval determined by this prior upper bound to pack all of the eigenvalues inside. So the goal, because we know 1 over x is discontinuous at x equal to 0, so we want to overcome this discontinuity, and we just want to fit our polynomial to be like 1 over x on the subinterval, and the shape of this polynomial outside d kappa is not of our interest. So once we can approximate 1 over x by a polynomial f on d kappa, we are able to use quantum eigenvalue transformation or quantum singular value transformation to implement the inverse of A. Let's take an example and see how the optimization-based algorithm works. So in the 0 step, it is initiated as a 0, and then in the first step, it will become something like 1 over x, and the uniform error bound is about 10 to the negative 3 or 10 to the negative 4. And as time goes, we can find the solution is more and more accurate, and it can achieve something like the machine epsilon. So one of the features of the optimization-based software is the QSP polynomial answers becomes very reasonable in just few steps, and the algorithm converges very quick to the global minimizer. Also, we can see another example. If we want to do the Hamiltonian simulation on a quantum computer, that means we want to map a Hamiltonian, which is a Hermitian matrix H, to be its time evolutional matrix e to the negative I tau H. And in the if you just focus on this eigenvalue transformation, that means we want to map a variable x to the cosine tau x and the sine tau x in a combination of them. And because the real and the imaginary part of the right-hand side are even and odd respectively, so that means we can use the polynomial to approximate this function up to some precision. And the theoretical analysis shows that the degree of the polynomial is almost linear to the simulation time. The simulation time parameter tau.
So Yulong,
and we,
quick question. Before you were previously mentioning that you can use the quantum singular value transformation to get an even or an odd polynomial, but this looks like a mixed a parity polynomial. Could you explain how that part ends up working?
Yes, thank you for the good question. So because this polynomial, because this function e to the negative I tau x is in general not of definite parity, we had to divide it into some kind of functions of the definite parity and to be real. So in this decomposition, we just use the identity to decompose it into a cosine and sine combination. And we are able to use a polynomial to approximate cosine and sine separately. And then we can implement the eigenvalue transformation of cosine tau h and sine tau h individually. And we use a technique called linear combination of unitaries to combine them together so that we can recover this time evolution matrix up to some scaling constant. Does it make sense?
Makes perfect sense. Thanks a lot.
Yes, thank you. And yes, so the numerical analysis shows that the time simulation time is directly related to the degree of the polynomial. And in our numerical results, we can find the optimization-based algorithm have a significantly less CPU times when running it to get the phase factors than other methods. So the numerical results also suggest that the empirical complexity of the optimization-based algorithm is something like d squared instead of d cubed in Haas or GSLW's method. So that is due to the observation I mentioned before, because in just a very few steps, the algorithm converges to a very reasonable polynomial. So the iteration step is similarly irrelevant to the degree or the shape of this polynomial, of the target. So, and another observation is, because we are using the standard double precision arithmetic, so the use of the classical base remains to be a constant. However, in Haas construction or the GSLW's method, they use a root finding subroutine, and they require a high precision in the roots. So they require more and more bits when the degree of the polynomial become larger. We also post our results in our code in GitHub repo, and you can download it if you want to do further developments. And the use of the toolbox is not very hard. And if you want to do the Hamiltonian simulation, you can just compute the phase factors in a few lines as in that example. So the optimization-based algorithm and the QSVPACK on the GitHub repo also streamlines the process of finding the phase factors. So if you are given a smooth function fx, it can be either a polynomial or not. We have different options to do so. So the first option is we use a traditional numerical analysis to obtain a near best polynomial approximation to this smooth function. For example, we can use Rame's exchange algorithm. And then we use the further numerical optimization to invoke this optimization-based algorithm to return the phase factors for us. And the second option is we can directly sample the smooth function with finite degree of freedoms. And we fed these samples into our optimization-based model. But numerical experiments turns out the second option is not very stable. So it inspires us that the existence of the global minimizer might be the key of the success of our optimization-based algorithm. And it also leads us to analyze the energy landscape of the optimization-based model. So the first observation is the symmetric phase factors are rarely important to the landscape. We just compute the smallest eigenvalue of the Hessian matrix near the optimal solution, and we find that if we don't impose the symmetric condition, then the Hessian is almost everywhere singular near the optimal solution. If we turn on the symmetric condition, and the Hessian matrix remains to be very well conditioned, even it deviates the optimal solution a lot. So the well condition is also shows that also means that the algorithm can be locally converged to the global locally converged to the solution we want. And if we investigate the landscape explicitly, we can focus on a very simple model. So we focus on we can focus on the degree 2 polynomial or the degree 3 polynomials. As I mentioned before, we can compute the degree of freedoms inside, and there are just two free variables, which means we can visualize the landscape explicitly on the 2D graph. And we find that so far the energy landscape is rather clean, and there is only global minima and no local minimizers trap our optimizers. But there are a lot of global minima, and we really want to find a way to characterize them. That is story I will tell you later. And if we if we go from the degree of freedom 2 system to the degree of freedom 3 system, we find the energy landscape becomes very ugly. And if we do a slicing on some kind of section of the optimization landscape, where we can easily find a local minima, and it is a contractor of the optimizer. That means if the optimizer gets close to the local minima, it will be trapped instead of escape from this local minimizer. And the previous numerical evidence make us to think whether we can find some simple uniqueness between the under the setting of the symmetric phase factors. And it turns out that if the degree of if we impose one more condition to the original existence theorem in GSLW, we are able to establish some uniqueness in our settings. So the first one is to match the dimensionality, because we only have at most d phase factors. So the freedom in the polynomial should be matching that in the phase factors. And the second is a parity constraint, because we can easily verify that the QSP formalism should have the parity constraint by using the transformation x to negative x. And the third condition is the so-called normalization condition. That is because we are, by using our SU2 matrix multiplication, the multiplied matrix is still in SU2. So if we take the determinant, we can get px squared plus 1 minus x squared qx squared. And because it's a special unitary, so it should be the determinant should be equal to 1. And the fourth requirement is the magic happen here. So for the case when d is odd, we have to make the leading coefficient of q to be positive. Otherwise, we cannot get the uniqueness. And it is the observation under the analysis by expanding returns and focusing on the leading coefficient of q. So if there exists a unique set of symmetric phase factors, if the polynomials pairs p and q satisfies those four conditions, then we can guarantee there exists a unique set of phase factors in some kind of set by quotient out some equivalent conditions, so that the phase factors and the correspondence between the phase factors and the polynomial pairs p and q are unique. And one immediate corollary of the previous theorem is we can find a bijection between the global minimizer, which is the phase factor exactly parameterizes pairs p and q, and all the admissible pair of polynomials p and q. By saying admissible, I mean they satisfy those four conditions. And consequentially, if we factorize px in the real and imaginary part, and we know that the real part is of our interest is fx, and the imaginary part is a p. I denote that p imaginary. So in order to explicitly investigate this bijection, we have to compute the complementary polynomials p imaginary and q. Those are real polynomials. And using the normalization condition, we have 1 minus f squared is equal to the p imaginary square and 1 minus x squared q squared. So in order to find fx, that means we should factorize the right-hand side as a single polynomial. So the right-hand side, it looks very viewed. And from this representation, it's very hard for us to imagine that it can be factorizable. And even further, we are not very clear whether there is a finite number of choices, these choices of factorization, or there's just an infinite number of choices for us to factorize these polynomials. And in the previous work, they just construct a class of solutions to do so. So the key of the success is to using the Laurent polynomials. And if we just do the variable substitution x from the real variable x and the complex variable z, we are able to replace our original polynomial to be a Laurent polynomials. And using the Laurent polynomial, we can rewrite the right-hand side as a product of two Laurent polynomials. Because each Laurent polynomial is factorizable, so this the right-hand side of this line is very important because it shows that the right-hand side is indeed factorizable. And if we properly choose a factorized form, we can directly set P imaginary part to be that corresponding to the polynomial of our interest and Q to be the polynomial of our interest as well. And if we pin down all the roots of the right-hand side, that means the set S should satisfy some conditions. Then it turns out that only finite number of global minimizers are there. So the energy landscape is not very complicated and can be somehow under our control. And our result also generalize the analysis based on the Laurent polynomials in the previous work. And we can find all the global minimizers. If we start from one initial guess, that is we call it phi 0, and this phi 0 is widely used in the QSVT for all examples. And the numerical experiment shows that this initial guess is virtually robust to all the target functions. If we just plug in plug phi 0 in the QSP matrix multiplication form, we are able to get the polynomial parameterized by this phi 0 is Chebyshev polynomials. So it's a very special solution for the case when the target polynomial is set to be 0. If we scale, because we previously only required the polynomial to be uniformly upper bounded by 1, but if we just relax it by some eta room, that means the maximum norm of f is 1 minus eta, we are able to investigate whether the problem is well conditioned in some region. So when eta is very, very small, the condition number of the Hessian matrix is very large. That means the optimization problem is rather is very singular and not robust robust against the perturbation. But if we scale eta to be something close to 1, then we can get a very well conditioned system. And it also make us to think whether we can find something by scale down this polynomial f. If we scale our 1 over x to be something like 1 over 4, the maximum value is 1 over 4, we can find the solution converge very quickly. But if we do not do any rescaling, and we can find the solution converges, the convergence of the solution is rather slow. To explain this numerical phenomena, we just cook up an example that is a degree 6 polynomial, but we scale is its maximum value by exponent 10 to negative k. And we use our previous theorem to explicitly construct the solution, the global minimizer corresponding to this polynomial fx. And we gradually scale down this polynomial and find there are in general 4 classes of limits in this example. And the first class is the solution I mentioned before, and we call it the maximal solution because it turns out that this solution have a largest convergence basin and the quickest convergence speed. So if we run our optimization algorithm directly from this initial guess, we can find the convergence rate of the first class or the maximal solution is the fastest one, comparing with all the others. And there are also some very good property regarding this maximal solution. So if we consider the distance between the global minimizer to the initial guess phi 0, it is upper bounded by a universal constant times a maximum norm of f, and the upper bound is completely independent of d. And this algorithm also suggests that the capitalization-based algorithm means we perturb our target polynomial by some small perturbation. This kind of algorithm doesn't work for the symmetric phase factors because the system is well conditioned. As a consequence of the previous theorem, if we set our maximum norm of f to be something like 1 over d, then we can consequentially get the distance between the maximum solution and the initial guess is also upper bounded by 1 over d. And furthermore, when compute the smallest eigenvalue of the Hessian matrix, we can find it is well conditioned because it is lower bounded by a constant. And the positive definiteness of the Hessian matrix at the optimal suggests that our algorithm can achieve some local convergence. And the last part, I want to quickly talk about another provable algorithm called matrix product state based numerical algorithm, optimization algorithm. So if we just dive into the structure of this QSP SU2 multiplication formula, we can find it can be viewed as a bound two tensor contraction. So the WX here is the X rotation, while the angle is constant, while the G is a Z rotation representing the phase modulations. And if we do the contraction, we are able to use a contracted result to represent an output of our QSP matrix multiplication that is ansatz of QSP. If we want to compute the gradients, we can group due to this symmetry, we have to identify this phi I and phi d minus I as the same variable. So we have to group the tensor into 3 different groups. And we just compute the gradient from the first one to the last one. And this round is referred to as a sweeping. And the sweeping-based algorithm, the theoretical analysis suggests that only d-squared computations are requested for each sweep. And by using this sweeping-based algorithm and using the tensor matrix product state structure of the problem, we are able to establish a theorem which shows the local convergence of our results. So if our target polynomials are upper bounded by 1 over universal constants times d tilde, then we can guarantee that there is the objective function is contracted by a constant in each step. And the inequality here also suggests that the number of sweeps theoretically should be something like d log 1 over epsilon. However, in the numerical observation, we find that the number of iterations is similarly very weakly on d. So the overall computational cost is about d squared instead of d cubed. And it also completes the story of the numerical numerical complexity of our optimization-based algorithm, because theoretically it should be D cubed, but numerically due to the weak dependence in D in the number of iterations, so the numerical cost is about D squared instead of D cubed. And and thank you so much for attending this talk. And I'm very happy to have any discussion if you are interested in our presentations or the work we did in this area.